for inviting me. And I know that I'm in the auto distribution session, so I have one slide about auto distribution, and then I'll give the talk. So the part of this work was done when I was doing my sabbatical at Stanford. This is the auto distribution. So I've been working a lot with systems folks and on resource allocation on networks. And for that kind of problem, you really need algorithmic alignment, a specific alignment to LP solvers to achieve some kind of auto distribution robustness, although we don't have yet a way to prove like bounds on the solution. So that I think that would be a very interesting problem to discuss in terms of algorithmic alignment in networks. And also there are some interesting extra equivariances for folks that like architectures for hypergraphs. Like there are different equivariances for hypergraphs. And also, if you like causality on networks, there is also a lot of stuff in causality for this type of problem. And the community is actually very, very interested, so much so that we had a panel in the main conference specifically to talk about how we can use ML in systems and make them robust, right? OK, so that's the slide on auto distribution robustness. And now I'm going to move on. So I've been writing forever, writing this thing, and it will come out on some mathematical framework for a graph foundational model, at least some view that I have. It's not a final answer to anything, but so I would like to start with some preliminaries. And what I'll do is I'll start talking a little bit about, for the folks that are not familiar with, symmetries through groups. So a group is just a set together with a binary operation such that its closure, there is associativity, there is an identity element, okay? And then there is an inverse, and that's a very important part of being a group, is that there is, for every element, there is always an inverse. And then how do we use this? We use this through group actions. So group action, essentially, I give you the group element, and then I give you some input space, and that acts, this group element acts on the space to produce some output. And then if you do it with the identity, essentially you get the same thing. And then a property of the group action is that if you compose transformations, so x is transformed by h and then by pi, I could do the group operation between pi and h first and then apply on the space. Okay, so that's what this is. I'm going to give an example to make this simple. So we say that a function is G invariant if the function is invariant to any transformation of the group. And then G equivariant if there is an associated way to transform the output if you transform the input and apply the function. Okay? So let's talk about G group equivariant and invariant neural networks. So consider F as neural network. It goes from X to Y, so 2 spaces. Then the equivariance is something like this. If I transform my input and apply the function, it's the same as applying the function first, and there is a way to transform the input to get that output. That's what equivariance means. And then these dimensions can be different, right? So applying on X may be a different dimension than applying on F. So this operator is appropriate for the space that we are talking about. And then G invariance is just that if I apply the transformation on the input and apply the function, it doesn't matter, I end up with the same output. So an example, a simple example, you think of triangle. The area of the triangle is invariant through translations, but the centroid is equivariant, right? So if you translate the triangle, then the centroid will translate equally, okay? So this is just to give an idea what invariances and equivariances are. So for graphs specifically, if I have an adjacency matrix, then I apply, say, a graph neural network, which is an equivariant representation for graphs. Then for each of these rows, each row represents a embedding for a node. So this embedding here on Z1 is the embedding for node 1 of this graph. But then if I do a permutation, I apply a permutation that permutes the first row with the first column, and permute the first node with the second node. Then I'm just permuting the rows and columns appropriately, right, in this adjacency matrix. And what happens with the neural network, because it's equivariant, I'm essentially permuting this, and then this is equivalent to permuting, just permuting the embeddings. Okay, so now that embedding that was on the first node is exactly the same vector, but on the second node. That's what it means to be equivariant. So when we talk about graph neural networks being equivariant, that's what we mean. Okay, so today I'm going to talk about two things. Very likely I'll be able to talk about this. Very unlikely I'll be able to talk about this. So one is a holographic node representations, and the second work is feature domain transferability. So let's talk a little bit about the tasks that these two works have. The first task is, if you think about the relational database, there are a lot of joint predictions that we want to do. So there are tasks like this, which are node level tasks, right? We predict something about the user. These are products with prices, and these are reviews, users and their reviews, right? Positive or negative. So a node level task is a task just of one node, and we are going to call it first order task. And second order task is, say, an edge level task. Yes, a joint task over two nodes. You can also predict two labels together jointly instead of predicting the labels separately. And that would be a second order task. Now we have third order tasks. You can think about predicting triangles, but also you can think about predicting these labels together jointly. So you just produce what they all would jointly be. And then there are fourth order tasks and so on. So for a relational database, there are a lot of high order tasks that you would like to predict. Okay, so not just node and edge, but also higher order. For the second part, the challenge is this. We have some features that are very different in different domains, right? So if I'm talking about a relational database, maybe I have some beds, and the beds have different set of features, right? Twin type, the material, the size of the bed, etc. And then if I talk about clothes, then there is the type of the color, there are different features. And I'd like to be able to use these features to train a single graph model. And more specifically, if we get to it, I'd like to train on this one and zero shot on this without ever fine-tuning or seeing this data, just zero shot predictions. We are going to, if we get there, we'll see how this works. So there are these two tasks. Why am I calling foundations of graph foundation models? I think that there are some interesting, like, simple principles that these models tend to have. So the first thing is, if you have more equivariances beyond node ID permutations that we usually do in graphs, then you can get a better generalization. So for instance, this idea of zero shotting over distinct attribute domains is an extra equivariance on the features, okay, that we are going to see. And also some older work on related to equivariances that are necessary for knowledge graph foundation models. And the second part is, a second principle is something that I've been very interested for a long time, is to unify positional and structural node representations. Things like eigenvectors and equivariant GNN representations. So how do we unify these things? And this is the work on holographic node representations. And if you want to understand better what this kind of task, why it's challenging, there is also this earlier work that we had done on the equivalence between these two types of embeddings. Okay, so just one slide on this. So if you, Michael was talking about knowledge graph foundation models. So the question is, what's the theory behind it? Like, why does it generalize over many different knowledge graphs? And the principle of all the work, so we have done this work, early work on double equivariance, and I'm going to explain what this is. And all the follow-up works are essentially all double equivariant neural networks. So they have the same equivariances, and that's why they are able to do these tasks. And the idea is essentially just defining what a symmetry what isomorphic graphs mean when you have different relations, okay? So what we are saying is that this graph is isomorphic to this graph. How do we do this? Is that we define an equivariance both on node IDs, which is the standard way to do equivariances on graph neural networks, and also the relation IDs. So if you think about this adjacency tensor, we have entity, entity, relation. And now we have an equivariance both on the entities and the relations. And if you build a neural network like this neural network sees no difference between these two graphs, right? Because the relation IDs don't mean anything. And that's essentially the idea. So the reason why all of this works is because it's based on this principle. Are we OK? Yeah? OK, so that's just this one example. Now let's talk a bit about transferability on joint predictions on relational databases. So this graph foundation model should be capable of pre-training on a diverse set of tasks, right, for transfer learning. So I want to train on node classification, on link prediction, on higher order predictions, and then have a disembedding train on all these things, right, of different graphs. So here is a question. It's a bit spicy, I agree. So, which is the following question. So here we have the standard graph neural network. Suppose that's most expressive graph neural network. And then we are training it on this node level task, okay? So we're trying to predict some label for you. And then the GNN produce use embedding for you. There is some MLP here predicting the downstream label, right? Now let's look at another task. Let's say that we are trying to predict edges. So we have these two graph neural networks creating embeddings for these two nodes, U and V. And now we have passed through the MLP and predict some joint property, right? For instance, if there is an edge between U and V. But why stop at 2, right? Second order. Let's do third order, fourth order. Let's try all the possible tasks we can train on this graph and other graphs, because different graphs will have different tasks. My question is, can we jointly learn a single graph neural network for all these tasks? Okay, we just use the same GNN. And maybe here what I'm saying, like it feels magical, right? It would be magical if we can actually do that. And the sad part is that there is no magic. Huh? Yes?
To clarify, so in the previous slide, are you just learning the GNN? That's
yes. So you can imagine that I have this as a loss, this is another loss, this is the third loss, this is the fourth loss, right. And I'm just training the same GNN over the whole thing.
And at test time, are you going to test in some different
I would test on a different task. Yeah. Actually, in our work, we do something like this. We train on this and test on this. Okay. We train on this and test on this one.
Okay.
So we do some transferability that way. But you just, even if you want to just say, I want to train on this 4, yeah, and then test on the same 4, can I do it with a single graph neural network?
Okay. It is the same graph.
It's the same graph. Suppose it's the same graph. Could be different graphs also, right? You train on different graphs. But imagine just make it simple. Let's train on the same graph. Okay? All right, so this is what this work is about, is how to do that. Is it possible, and how can we do it? And before this, I have to explain some of the definitions. This work is an important work, I feel, that explains a lot of how these tasks are different and the difficulties in doing these tasks. And recently, we wrote a blog post, which is in the website, explaining the difference between structural and positional representations. And I think it's quite instructive to understand what I'm going to talk about. So it formally defines positional representations and the notion of distributional equivariance. So it's equivariant in distribution. It's not equivariant. It's in distribution. And defines how structural representations perform k-node tasks, so like tasks on multiple nodes, 1, 2, 3. Okay, so let's talk a little bit about the differences. So I have this one graph that has two disconnected components. And suppose I run some embedding, and I get this output. And the output, the colors are the first three dimensions of the embedding in RGB, okay? So you are seeing what the embedding looks like. And then we run a second different function for the embedding in this graph, and this is what we get, okay? Different embeddings, you see very different properties. And the top one we call structural representations, and the bottom one we call positional. And then I have a question. So there is a homework. And the homework is, OK, so this one, is it Laplace eigenvectors, or is it a vanilla GNN? And this one, is it Laplace eigenvectors or a vanilla GNN? By just the properties of GNNs, you should know. Yes? You can answer, you can answer. A is what? Laplace? Vanilla GNN. We agree? No? Yes? 1, 2, 3? Yes. So the thing is that GNNs are equivariant, right? These nodes are isomorphic. So they have to get, by definition, the same embedding because of the equivariance, right? And eigenvectors are not equivariant. They're equivariant in distribution. So they don't have that constraint. All right? Are we good? Yes? All right, so, OK, so essentially what happens with eigenvectors is that they break symmetries. So the symmetries that we see in the graph are broken by eigenvectors, OK? And that's very important to understand. So the work on structural node equivariant representation, we have all the people that have started this in this room, which is great. Essentially explaining the equivariance that GNNs create. And then in the work that we have, we talk about what this really, like some consequences of this. Now, one of the consequences of this is as follows. And it's pretty easy to see. Consider that I'm trying to do some link prediction on this graph, OK? So this node is isomorphic to this node. So a GNN will, because it's equivariant on nodes, will give the same embedding for both of these nodes. OK, so the embedding has to be the same. Therefore, if I'm trying to predict a link between 0 and 1 or 0 and 7, I cannot distinguish them. They look the same. So if I look at the embedding for 0, and then I apply a function with the embedding for 7, the output has to be the same as if I apply the function with the embedding for 1. Right? So it doesn't matter that the GNN is most expressive. There is a limited expressiveness for predicting joint tasks. OK? And that's the problem that we are going to have when we try to learn one single GNN to do all these tasks, because the symmetries required for each task, they are different symmetries. They're not the same symmetry. OK, so let's then go with another case. Suppose I have this task. And the task is that here we have edges, and here we don't have edges. And we are trying to run a GNN to predict this, OK, this node equivariant GNN. So here's a challenge, right? So the rule is that if you have more than 2 common neighbors, you have an edge. If you don't, then you don't. But if you look at what a GNN would give as an embedding for this node and this node, because it has to look at the structural properties of the neighbors. And the structural properties of the neighbors look very similar from here and here. So what happens with a GNN when you try to do link prediction is that it will overfit to some weird thing about the structure that you see in the training data, right? Because otherwise it cannot predict that there is no link here and there is a link here. Structurally, the neighborhood looks the same, right, if you were to build the computation graph. So that's what we actually see in practice. In practice, they overfit to the data, and it becomes very challenging to predict links. OK, so that's for node equivariant. And that's what I said is essentially like they tend to learn shortcuts. They look at degrees, features to try to distinguish the two cases, but they really can't. It doesn't work well in test. Okay, what about positional representations? Let's forget, so we can say, well, then equivariances are not useful. Let's go with positional representations to do our tasks, right? Say Laplace eigenvector, right? We get these distinct embeddings. And also, more than this, like one of the, at least the one that I know, the first work on talking about using some unique node features to break symmetries on GNNs so they can get some kind of positional node embeddings that will look more like this, is this work on positional aware graph neural networks. And essentially, all the works that came after are the basic idea is that you put some special feature on the nodes to break the symmetries and then be able to predict links. Okay? And nowadays, this type of notion is called labeling trick. And one of the best methods for this is the Neuron-Bellman-Ford algorithm for link prediction. So that allows the GNN to break the symmetries, and now it's not equivariant anymore, and then you can a bit solve this problem. And the idea is pretty simple. For the source node, you put a special feature. And now if you look at, can I count the number of common neighbors? You can. Because this node here, for the second layer, it can see that it has this reached this unique feature. Therefore, there must be 1, 2, 3, 4 common neighbors. It can count those. And that's what allows you to do link prediction, for instance, in this case. But more generally, it's a joint representation between U and V. That's what it creates, because it's conditional on U. Yes?
So I thought these methods with the labeling were still equivariant, theoretically at least, because you're trying all the labelings and all possibilities, and then aggregate against.
No. So yeah, if you do random labels, it's not equivariant because they always break the symmetry. So this node would not get the same as this node because it's very unlikely that they get the same random feature. That's one. The other thing is that if you do for the source node, then this node would have a special marking, but this node wouldn't. So in the end, this will get a different embedding than this one. So it creates the symmetry break. Essentially, the basic idea is to create positional representation with symmetry breaking labels or features. Okay, so, but this creates a joint representation. That's very important. It doesn't create a representation just for U or for V. It creates a representation for both. Okay, so then, either through trying to do positional representations or through just trying to run equivariant in some kind of equivariant for just a node. I'm not going to talk about what equivariant for joint would be, but this is an example of equivariant for joint of two nodes. And then you try to do for higher orders. What we can prove is that if this F here is an MLP, this is impossible. We cannot do this. There's no way to do this. You cannot learn one GNN for everything because the symmetries of the tasks are different. So you end up with the wrong symmetries for some task. Yes?
Even with the symmetry breaking?
Yeah, even with the symmetry break. So the thing is that, imagine like for case of marking the source node. Here I mark the source node, I get an embedding, right? Here I mark this source node, and I get an embedding. If they were isomorphic, I still get the same embedding. And if I do just for U, joint with V, then this task here, the model is confused about what U is, what V is. So really, there is no, either you do for joint or you do for, because the tasks on graphs, they are for a specific symmetry. And the symmetry is for the number of nodes you're talking about. And you really difficult to do all the symmetries. You cannot do all the symmetries together. Yeah.
But you would expect for this higher order cases that you need more than one label, right?
Yes, exactly. Yeah. For the higher order case, you would need two labels, and then the symmetry is different than this, and makes it really difficult. So it's a very interesting problem, right? Because there's this impossibility of satisfying everybody. Okay, so so what is our work about, right? I just said it's not possible, so I guess that's the end of the talk. We can now go home. So what we do is as follows. We essentially break the problem down to two parts. And that's why we're calling holographic node representations. So the easiest way to describe, it sounds a little weird, but then I'll explain why, is this generalizes the notion of eigenvector and eigenvalues to GNNs. And I'll explain what this means. So first, there is an expansion map that generates a high-dimensional task-agnostic representations. These are positional node representations. They don't have any equivariances, okay? They don't have any equivariances. And then the labeling trick used to do them is graph and task conditional. So they are depending on the task in the graph. And I'm going to explain what this means with an example in a second. And then after we create these positional representations, which are multiple embeddings, not just one. So, and also they are varying sizes. For different graphs, they may have different sizes. We have a reduction map that recovers the equivariance needed for the task. So you get these positional representations, and this reduction map essentially is recovering the equivariance that you need for link prediction. Here would recover the equivariances needed for node classification from the joint from the positional representations that broke all the symmetries. And then we can show that we can create k node equivariant embeddings with this procedure. So we can have larger, not just 1, 2, but 3 nodes, 4 nodes, 5 nodes. Okay, so to explain this, I'm going to use eigenvectors. So we are going to do this in the Lanczos algorithm for eigenvector computations. So how does this actually? So how does Lanczos work? First, you start with some random vector. And this, in SciPy, this vector is a standard normal that it randomly samples. And this random sampling breaks all symmetries of the graph. That's how the algorithm starts breaking all symmetries for no reason, because you don't have to break all symmetries. You don't know if you need to break any symmetries. So there is no need to do that, but it's easier, right? So instead of doing this, what we're going to do is that the first initial vector is going to come from an embedding from a GNN. So it's going to be equivariant. Okay, so, and the interesting thing about the Lanczos algorithm is that if you start equivariant, the output is equivariant, because the algorithm itself is equivariant. The reason why eigenvectors have ambiguity is because of this. That's what starts the ambiguities of eigenvectors, is the random sampling. Okay, so then what happens? Well, there's no magic. If I start equivariant at some point, maybe I don't get a vector that is orthogonal to the subspace spanned by the current vectors that I have. Although Lanczos doesn't compute eigenvectors directly, but let's assume that it does just for simplicity. So this will happen, for instance, when we need to break symmetries in the graph. So look at this graph. For instance, we have this node is symmetric, is isomorphic to this node, isomorphic to this, isomorphic to this. At some point, by starting with the GNN, I'm going to stop here. Because these eigenvectors, I cannot get them to be different. Because they are equivariant, right? I started equivariant, the algorithm is equivariant, so I cannot get them to be different. And then what happens in SciPy is that at this point, they would, again, sample a uniform to break the symmetries, break the symmetries that still exist. But instead of doing this, instead of doing a random symmetry breaking, right, randomly putting some values in the vectors, we are going to have a specific way of breaking so that later we can reconstruct the symmetries when we want. Okay? So we are going to look at the symmetry according to the GNN. So the GNN told us that some nodes might be isomorphic, and we are going to look at those. Maybe they are, maybe they aren't, but we're going to break those symmetries at this part of the algorithm. Okay? So we are going to break one of these nodes, and this is what creates multiple embeddings, because for each isomorphic node, I have to break for each one of them and compute the eigenvector for each one. So I get multiple, essentially, eigenvectors from it. Okay, so we repeat for all the GNN, the isomorphic node that the GNN said are isomorphic, essentially gave the same embedding for all of them. Okay? So in this case, for instance, we are going to do this 4 times. So we got 4 vectors, 4 embeddings, Laplace embeddings for the nodes. Each node will get 4. Okay, so then we have 4 isomorphic nodes, for instance. We're going to have 4 positional node embeddings that are these eigenvectors. And then essentially, if we're talking about, you can think of like 4 different labeling tricks, right? Because we are breaking symmetry by perturbing the vectors. Okay, so now one interesting thing is that for a specific task, you don't need to break all the symmetries. So we can be smart about it. We don't really need to break all isomorphic nodes. And how do we generalize this idea, right? So I'm talking about eigenvectors because I find it a bit simpler to explain. But any function that is node equivariant can be used. So Lunch's algorithm, a GNN, power method, or the QR algorithm, there's some details of how to do that, can be used, like any such method. And for eigenvectors, you essentially get some kind of canonical eigenvectors from it. Okay, so then there is another part, which is for all the nodes that were the kind of symmetry nodes that you had to break together, you had to choose one by one, you have to tell them that these, for the reduction map, these need to be used as a set. So when you use these embeddings, you have to use the embeddings as a set of embeddings because there is no specific order. The way that you broke the symmetries is arbitrary. So you need to remember this is a set, and therefore you give the same number for all those vectors. And this in eigenvector space would be the multiplicity of your eigenvalue. Because your eigenvalue is the same, it's telling you that that subspace is essentially, there's no ordering to that, right? And this creates also the same notion that these vectors are from the symmetry breaking, therefore they need to be treated as a set, right? So when you use the GNN, for instance. Okay, so the idea is to break the symmetries through the expansion map, and then keep track of how we break the symmetries to restore them through the reduction map. So essentially, like for eigenvectors, for instance, you don't get wild eigenvector ambiguities. The drawback is that you're not going to do all breakings because it's exponential. So you try to contain this, right? You're not going to. Otherwise, we would have a graph isomorphism doing this, but we don't, because it's too expensive. Okay, so, and then there are another way to do this, this representation, which is faster, is that we break all of them in parallel. But then there is some loss in expressivity when we do that. Okay, so then, so now what we have is essentially, going back here, so what we have is that these embeddings are all positional, and the reduction map predicts links, can predict node representations, and these embeddings can later be used in other tasks, higher order tasks or lower order tasks than what you have trained, right? So for instance, we are going to train on just node and then try to use the embeddings to predict link. Or we train on link and then try to use embeddings for node. We train on node and link and try to use for higher orders, like 3 or 4 nodes. So this is what the graph looks like. So if we pre-train on link and predict node, then we can see that holographic GNNs have a very small loss between the pre-trained, when you pre-train and use the pre-trained model, and if you train from scratch on the actual task of link prediction. And you can see, for instance, if you do any of the link prediction methods that you're trying to use to train for link prediction, they are pretty poor for the node representations. They have a big gap between using the pre-trained embeddings to training directly on the task. Okay, so essentially what this plot is showing is kind of the gap that exists with what we can do with standard methods and what we can do with holographic node representations. Are there any questions? Yes?
Can you explain a bit about this dimension of this?
Yeah, so here we have these different Yeah, so these are different embedding methods for the nodes. And here is the task that it was pre-trained on. So this was pre-trained on link prediction. And then we use the embeddings for node classification by just training the MLP. So we get the node embeddings frozen, and then we train an MLP to do node classification. So you train for link prediction, the embeddings are frozen, and now use those for node classification. And then there is a big gap in performance because the methods are learning the wrong symmetry. So the link prediction methods learn link prediction symmetries, which are wrong for node, and the node methods are learning node symmetries that are wrong for link. So then you get this kind of gap between them. For some methods, the gap for GNNs is larger than others in some different tasks. And here is a task where, for instance, we train on the worst pre-training task, which is either node, link, or higher order. And then we have a task that is joint to predicting just 2 nodes. Here predicts 3 nodes. So the two users watching the same movie jointly. I want to predict these 2 links together. And here we want to predict whether the 2 movies will be watched by the same user together jointly. Okay, so this is the task that we have, and this is the worst pre-training that there is in the data that we can do. And then we freeze the embeddings, and then we try to do this task with just training the MLP over the concatenation of these embeddings. And you can see that essentially you have a big, so for a GNN, there is a giant gap between what the GNN is capable of doing, which is essentially because the equivariance is just really node classification, and the higher order tasks that you can do. Especially if you get this task, which is a higher order, which is a difficult task, you see a giant gap. Yes?
In this movie case, it's always the same, say that if I pre-train on the same task, it gives me the best accuracy on the same task?
No, so you pre-train on some task, the worst task. Imagine that the worst.
So basically, question: can it get better?
Sorry, I don't.
If I pre-train on another task, can it get better on my task?
Yes, it can get better on your task. Yeah, that's something we are looking into. What are the right tasks to pre-train so that it's kind of robust to things that you want to do in the future, right? Higher orders or different tasks. There's an interesting question of what's the right task to pre-train.
In theory, if I pre-train on a better task, it will include more information than I wish for.
It could be, but here's an interesting aspect of this, is that if these embeddings, they have more information than you need, the map could remove them. Yeah. The map actually removed the symmetries that you don't need. Because we broke all the symmetries. This is positional, right? And it's restoring just the symmetries you need for this. So for node classification, it removes all the symmetries that are not equivariant in node. And here it removes all the symmetries that are not equivariant in both nodes. So it does that. Yes?
That link reduction map, is that hard-coded or trained? Like you want edges and then you know what you have to remove?
Yes, you know exactly. Like from the way that because the way you know how you broke, then you can create an architecture that recovers the right equivariance for that. So it's hard-coded the way that you do it.
So for this movie recommendation test, do you also compare to methods which are not graph neural networks? Maybe I just missed it.
It's difficult because a lot of the non-graph neural network methods are positional, and then they will not do well on node, because node really requires equivariances.
Okay.
So for instance, if you use eigenvectors, right?
Yeah.
So have a question, right? Have you ever seen a paper using eigenvectors for node classification? Have you ever in your life seen a single paper using eigenvector for node classification? You have?
Not like.
Does it work?
As a baseline.
Yeah, but does it work? No.
For some graphs, it's.
Yeah.
Wavelets on graphs, which are also...
You see, the reason, you see what the reason is. The reason is that you broke all symmetries. Now for node classification, you need them back. And for eigenvectors, because you have this wild breaking of the symmetries, it's really difficult to get them back.
Yeah, but they work well for community detection, right?
Yes, but the task in community detection is not a single node task.
Yes, exactly.
Yes, that's the thing.
Right? So
Well, we can talk about this. I can tell you everything about it. Like, I thought about this problem for a long time. So, like, yeah, for instance, if you want to find communities, right? A community is not a single node task, it's a multi-node task, right? And for that kind of task, this break of symmetry is fine.
okay, so that's actually the very far and a half of
Very
the
far,
end
yes,
task
yes,
in your
yes,
slide.
yes,
Okay.
yes, yes.
Thank you.
I am not doing that, that's too hard, right? So GNNs for finding communities is very difficult because it's a task that's variable size and many nodes. So theoretically, it's very hard to do with GNNs. You have to break the right, we don't know how to do that. At least not theoretically sound way. Okay, so yeah, so that's, so essentially, you see, like, the thing is that for eigenvectors or positional representation, we broke these things kind of randomly. But if we break in a certain way, we can recover the equivariance, the right equivariances. I think that's what's very interesting about this work.
So is there any relationship between this individualization refinements technique and Graph-Weiser?
It's related, yeah, it's related, but for the notion of graph isomorphism, I don't really understand the relationship between, like, the different equivariances that you have.
Oh, but I think if you have this slide where you have these different algorithms that you could plug in, if you plug in color refinement, I think what you're having is...
Right, yes, yeah, color, yeah, you could recover equivariances for color
Because you're
refinement.
just introducing new colors
Yeah.
every time you have a tie.
Yes.
So if the eigenvalues are distinct, then the eigenvectors are unique up to flipping the sign, no?
Yeah, they could also rotate.
But if the eigenvalues...
Oh, no, the eigenvalues are distinct, yes. But then you don't have any symmetries in the graph. And then yes, you don't have any symmetry. So you can make them canonical, actually, right? So don't use SciPy because it will create these signs,
Yeah.
random signs. Do this, and then there will be no random signs. So you don't have to do with those. Which is pretty interesting, I find. Yeah, okay, so I don't know how much time I have.
15 minutes.
15? 1-5? Okay. Do we have more questions on this? I can quickly go through the feature domain transferability. So graph foundation models should be capable of pre-training on a diverse set of feature domains, then zero shot of fine-tuning new feature domains. And that's the question that we have. Whether this can be done for molecules and then you train on molecules, you do social networks, I don't know. Don't ask me that question. I don't know. I'm going to give you a very constrained way. What I'm interested in is building a method that can do this. Whether it works is a separate question. So this is the work. Harry Laus is a co-author here. Okay, so I'm not going to talk about this. So if you're doing PC, you can think about doing PCA, ICA. It's hard to do, or some kind of inverse mixing model. It's kind of do for categorical features, and we can talk offline, and I'll tell you why I don't really like. I think there are some restrictions on those. But what I am interested in is, I've been studying causality, and then one of the main things is this idea of independence tests, right? Is a variable, random variable A is independent of B. And then there are this distribution-free independence tests, right? Which, for instance, a rank test is a type of independence test. So suppose you have a joint distribution, you sample the ID, and here's a table. And then what happens with, say, a rank test is that instead of using the values, you're going to say, if this is the third largest value, this is the largest value, this is the smallest value. Essentially, you replace the numbers by the ordering, okay? How big they are. And then if this is, if this is what we call totally ordered data, right? So the order of the data is important. Then I do this. If the order of the data is not important, then I don't care, because on ordered sets, it doesn't matter what the order is. Okay? And then what a permutation test, what this distribution-free independence test will do is essentially they permute just the column B, for instance, and they ask, do I see any difference, statistical difference between this table and this table? So I have some measure, some metric over the tables, and then I measure if the metric looks different, if I just permute this column. Why permute this column? Because then I make B independent of A, right? Just by permuting the column. So essentially what a rank test, and actually this is started because I was reading this paper from Sibel, and then he was talking about that all distribution-free procedures are based on permutations, essentially. So you can reduce anything that you know to essentially a permutation-based test, okay, on your data, similar to what I was talking about. And then I started thinking, well, if the data is not IID, right, not independently sampled, but rather is in a graph and I don't know the dependencies, then what can I do with this? And could I do some kind of message passing to tell the other nodes what how dependent my features are to their features? Because if I can just talk about dependencies, the feature values are not important. They're completely irrelevant, right? So here is the thing. Suppose that, since we are just talking about permutations, suppose that I just put all the invariances on this task, this distribution-free task, on my data. Put all of them. How am I going to do this? We are going to do this with this feature hypergraph, okay? So I'm going to order the nodes from largest to smallest if they are totally ordered. And if they are not totally ordered, I don't care. And then I create these hyper edges between the features. So these two are essentially sampled together. These two are sampled together. And now what I'm going to do is I'm going to run a hypergraph neural network on top of this to represent this data. But there is two invariances that I need. First, I don't want invariance here because the order of this data is important. So this will be permutation sensitive. Since this is unordered, this is not permutation sensitive. And then I'm also going to say that this is not permutation sensitive because the order of the features is not important, okay? And this captures all the invariances that a permutation test has. So this is distribution free, testing whether the dependencies can test, this can provably test the dependencies in the data. And what we will do is like we can connect this node to this node and this node to this node with different types of edges, and you could just run a GNN on this with these features, right, from this hypergraph GNN. So this is one way to do it, and you can even make this most expressive if you are courageous. But this is too expensive to run. So we do this for these features, but we do it for all the features. Essentially, we are connecting the nodes to the right features that they have. Okay, so you can prove that this feature hypergraph is most expressive for distribution-free tests. If you have a most expressive hypergraph GNN with the right permutations, the right symmetries, right permutations. But because this is incredibly slow, in the paper we simplified a lot and lost a lot of the expressiveness. I'm not going to describe how we simplified that, but we did something simpler. It's still a little slow. We are trying to make it faster, but it loses expressiveness. Ideally, if anybody has any idea how to make this extremely fast, I'd love to hear you, because that's really what we should do. Okay. And then what happens is that suppose that I train, I'm trying to predict what people will buy, okay? And I'm going to do this zero shot, meaning I'm going to train on what people buy on desktops or user products, refrigerators, smartphones, shoes, and clothes. And I'm going to train on this data. train the model on this data, and 0 shots to predict beds. Beds has all those features that you saw. Is it a queen, full, height, all this. And what's interesting is that if you look at the predictions that this method does, it's way better than doing structural features alone or any kind of encoding, LLMs, whatever you do. You have a much more accurate prediction doing this. And we have also done, for instance, for this graph here, we pre-train on all these things and test on closed. These are not closed. It has no features like closed. And then you can see how much more accurate this is because it's actually using the features. So how is it possible, right? How is it possible that I'm training on beds and then I predict on close? It's because in the network, because of these equivariances that I forced the network to learn, it doesn't care about the values of the features. It all it cares is how the variables are dependent to predict my task. So essentially, I'm learning the right type of permutation test, or the right type of hypothesis dependency. Sorry, I'm running the right type of dependencies to predict my task. And then if the dependencies are similar for all these tasks, which are people buying things, right? Then you are able to predict. So then the features themselves are not important, the values of the features. Now, of course, if the feature sizes are very different, it can be challenging, right? Because size invariance is a difficult thing. So there are all sorts of things that we have not analyzed yet. But I think that as a first work doing this, I find it very interesting to kind of move away from using features to use dependencies. We also have done this for social networks and with some baselines. And the only feature that's the same is age. But if you put age, in the appendix we put age in the graph neural network, it is not as good as predicting with this procedure. And also, the other thing that I find important for this type of work is to show that as you give more training domains, right? You use beds, now use smartphones, now use beds and smartphones, now use beds, smartphones, and desktops, then your predictions improve because you're learning with more domains. Therefore, it's kind of a meta-learning problem, right? The more data you get, the better you should do in the tasks. And you can see that as we get more training domains, the predictions become a little better, but lower variance. Any questions on this part? I know I went a bit fast. We can talk about, yes?
So can you explain a bit more? You say you're encoding dependencies.
Yes.
So I guess, yeah, maybe a little bit more.
What Bell shows is that any function that has these invariances is a test. Okay, some test of dependency that you're doing. Okay? So what we did is we said, okay, we just put these things on the neural network and let it learn. Because if you build your function, you have to assume independence. You have to assume something to build a function that makes sense, right? But a neural network doesn't care about any of this. I just put the right invariances that an independence test would have and just let it learn what it needs to learn. Each
task, like your bed, your GNN.
Yes, it would be one hypergraph, right? And then there is an embedding that it creates for each node.
I see.
And then if I change the features, then it creates another hypergraph, and there'll be embedding for this node for that other hypergraph. And then what it's trying to learn when you give multiple of those, is trying to learn something that's invariant over all these different hypergraphs. Right?
So even when you change a node feature, it's basically just the corresponding nodes in a hypergraph has a slightly different representation.
Right. So you can imagine,
are the same. Like the edges, there is some shared edge structure.
It's like a graph classification, right? We give different graphs and we say, oh, this is one thing, this is another thing. So imagine like abstractly, like you are trying to do this hyper edge embedding and use all these hyper edge embeddings here to predict something. And then you change the features, the embeddings change, and the neural network learns how to be a bit invariant to those changes.
I see.
And that's where it tries to learn that. And because we gave the right permutations, right, the right invariances, then it's really trying to learn dependencies.
I see.
Yeah.
Thank you.
So sorry, also to understand this a bit more, is the idea that you want to learn how to ignore feature values when they are not helpful, but still maintain, because you could also kind of remove feature.
Right, remove all the features.
Remove them, right?
Right. The baseline is removing, one baseline is removing everything. Yeah, so we are not trying to remove the features, so we are trying to be invariant to things that are not the dependencies needed to predict the task. So for instance, here, there is an ordering, right? And I'm using the ordering.
So the point is, your hope is that in some zero-shot tasks in a new domain,
right,
you need, so some of the features might actually overlap or be helpful, or
they don't overlap, but the kind of hypergraphs that you tend to see, the embeddings that you're learning for those hypergraphs, if you have seen enough tasks, it will not be that different from what you saw in training. That's the hope. But we cannot prove that, you see, because we don't have it would be interesting to have a theoretical, clear, like assumption, right, in which you can say, oh, under these assumptions, definitely you can do this. Does that make sense? Yes.
So you're assuming that all the tasks are distribution free?
Yeah. So it's not assuming they are distribution free, because they are not. It's just that if I want to zero shot, I need to learn something that's distribution free. Like if I'm doing, you see, like this could be your shoe size, or could be the size of your iPhone screen. Because on phones it would be size of iPhone screen. The other one could be shoe size, or could be something else about.
Like the graph that you had, I think the next slide.
Yes.
No, I don't. The results that you had was.
Oh yeah. This.
How do you know these tasks are not from the same distribution?
These are bads, and these are. I don't know what distribution means. The features are totally non-overlapping. Like these are close, and these are bad.
They come from a similar distribution.
I don't know what that. They don't have the same domain even. This is twin, queen, king. The size of the bed, the size of the post. This is your clothes size, and the color, and the appearance, and the material. Like they don't overlap.
I guess the question, maybe if I understand, is if I forget about the words,
yeah.
I just say I have a normalization function that map these things into, say, numbers. Maybe they get to map to a very similar distribution of numbers.
I don't see how that, I don't know. I don't see how that's possible, because some of these things have just categorical features, right, and some of them are continuous.
Okay.
And they have different number of continuous features.
Okay.
And some are discrete or not, I don't know.
Okay.
There may be some, it's trying to learn to project this thing into some space, but you can't look at the feature values because they are so different if you do some kind of inner product with it.
Right,
It's too hard.
It's maybe more looking at the similarity of the hypergraphs.
Hypergraphs,
like
yes.
Structure.
Yeah, exactly.
And also they're ordered, right?
And when they are ordered and when they are unordered, so it makes a difference for the features, yeah.
Yeah, but I guess like what Stephanie just said, how do you know like the graph that the table that you have doesn't have an intrinsically similar correlation structure? Because I think what I understand.
No, there is some dependencies that are. You see, we are trying to embed these hypergraphs in a way that the embeddings look similar, so that I can capture the dependencies between the features and my task. That's what I want.
So you're trying to make something that's foundation models. I'm guessing you're trying to.
Oh no, I'm not gonna. Okay, maybe. So I am not claiming that we can do everything.
Okay.
I'm just saying that we have a tool which we can apply to do things. Whether it will work on everything is a different question. Molecules and people, I don't know what law of nature would that be. I haven't tried, maybe I should. Right? So I don't know. But we have a tool to do it if you want. And the end of the thing, I know that some folks are quite skeptical about graph foundation models, but I think what I find it interesting is that if we have this task as a goal, which may be impossible, we will find new tools and applications. I think that's the interesting part, because it really allows us to think a bit outside the box. And that's what I like about the graph foundation model.
Okay, let's thank the speaker again.
All right, thank you.
We have one more talk by Soledad.